In this lecture, we're going to talk about single unit processes, and we're going to talk about the procedures for putting together a mass balance. So very procedural, very much about how we actually do this. And then we're going to throw in this concept of degree of freedom analysis that we're going to use later through the semester in order to help us figure out if a problem is actually solvable. So let's move on. So first things first, when we balance continuous steady state processes, there's a couple things that we can do. So if we know that a process is steady state, accumulation has to equal 0. That's our definition of accumulation in steady state, right? So what that means is that the general balance equation simplifies down to input plus generation equals output minus consumption. And all I've done there is I've moved the output and consumption terms to the other side of the equation, so everything has a positive sign. And then remember, if the balance on a non-reactive species is on a non-reactive species or on total mass, we can say that the input is equal to the output in that given system. Okay. Now, why is this the case? Why are we allowed to do this? Well, we have the law of conservation of mass. For any closed system, any transfer of mass and energy, it has to be remaining constant over time because the system's mass can't change, so either quantity can be added or removed. It has to be conserved. Same with the conservation of energy, right? The total energy in the system is constant because energy and mass are related. That's E equals mc squared, right? That's how they're related. So both those quantities are conserved. So remember that steady state or continuous means that the variable doesn't change with time. So remember, when we have the general balance equation and we're simplifying it, we want to hopefully get it down to something where the input equals the output, or something at least a little bit more easy to deal with. So if accumulation equals 0, that's a good situation for us. When we have balances on batch processes, we have something that's a little bit different. So the accumulation in a batch process is going to be whatever the final output is minus the initial input, which can also be defined as the generation minus the consumption. So there's going to be two types of accumulation that happen in a batch process. So in a batch process, when we do a mass balance, the initial input plus whatever the generation is going to equal the final output plus the consumption. Now, in a batch process, for the purposes of this class, when we're doing single units, you only have one input and one output. And that's why we're giving these final and initial states, because remember that after some time, something comes out of a batch system. So it looks a little bit different than our other general balance equations when they're simplified, but basically what we're saying here is that a batch system has a unique condition where we're looking at the initial input and the final output. When we do balances on semi-batch system, the process here is to write a differential balance on the system and then integrate between two instants in time. Now, we're not going to see many semi-batch throughout the semester, but we are going to talk about the accumulation of volume in certain systems. So when it comes to semi-batch, we need to take a process that's a little bit different. So we'll go through that in detail as we need to for given problems. So let's go through a very, very simple equation where we take the general balance equation and we apply it to population dynamics as a way to start looking at how this general balance equation matters when we're looking at the system. So let's say that each year 50,000 people move into a city, 75,000 people move out, 22,000 are born, and 19,000 die. And we want to write a balance on the population of the city. Now, if we're looking at the period of over a year, that is going to be a system where it's not changing within that year, right? This is per year. So that time element can sometimes be a little bit confusing. So we're looking at how many people per year. And because we're looking over that year time frame, we can kind of treat these numbers as if they're just numbers of people. So that's something that we're going to do to simplify this problem. So let's talk through this problem, because as we start to do single balances, we need to really understand where the inputs, outputs, generation, consumption, and accumulation terms are in these problems. So one trick that I like to use is what I call my highlighting technique, where I like to change the colors of the words or highlight them in different colors to try and make them stand out to myself as I go through. So here is how this is going to work out. When you have this particular problem, you need to first define what is going on in the problem. What is your system? So I'm going to define the system as the city for this particular problem. If I were to say that the system is people, that makes no sense. There's no way that we can do a balance. But if I can say the city is the boundary, then we can actually do a mass balance. So if people are moving into the city, they are crossing the system boundary, which means that the 50,000 must be an input. So everything that you see on the screen that's in purple is related to that input. When we have the 75,000 people moving out, they are crossing the system boundary again outside of the system and leaving. So they are actually the output term. So everything in orange is related to output. The 22,000 that are born within the city. So if you are born within the city, that's a positive uptake in population, which means that's the generation term. So everything that you see in light blue is related to generation. And then 19,000 die, and that is within the city. Again, so remember, if it's within the process, it must be either the generation or consumption term. Now we know that if we have people dying, that is a net loss of population. So anything in green is going to be related to consumption. So if we're looking at the number of people per year, we can take input plus generation minus output minus consumption equals accumulation and plug in all those numbers to find whether or not we are net gaining people in our city or net losing people in our city. And it turns out in this case, we're actually net loss of a population of 22,000 people per year. So we actually have some loss of population over time. So the purpose of this problem is to get you thinking about how do I highlight what's in the problems and how do I write a mass balance. Now, one thing that you want to take note of here is that we are writing the mass balance on the people. There's nothing else here, so the people are considered our species, so to speak. So in this particular problem, we're looking at number of people in and out. There's only one species. But this becomes a little bit different when you have multiple species in the system. When it comes to mass balance procedures, one of the things that we might want to do is perform what's called a degree of freedom analysis. And what a degree of freedom analysis is meant to do is it's meant to help determine whether or not there's enough information to answer the problem. And this is important because in the real world, we may not have the information that we need to actually solve a real world problem. You would hope in class that every written problem that I give you has enough information to solve, but that may not actually be the case. And one thing that we need to be able to do as engineers is figure out if we have enough information to solve, and if we don't, how do we find that information? So let's go over briefly how to perform a degree of freedom analysis, and we will take time in class to apply this. So first thing that you need to do is what you've already been doing. Draw and completely label a flow diagram. Then you need to count the number of variables that you have that do not currently have numeric values. And this is part of the reason that we need to write everything out in variable form so that we understand exactly which does and does not have a number. Then we need to calculate the number of independent equations. So we need to figure out how many equations don't rely on relationships that are present in other equations that we've written. And we'll talk about this in detail in class, but basically the idea is that in the equation, your dependent variables cannot be part of another equation and be considered independent equations. When we do our degree of freedom analysis, there are three possible outcomes from the degree of freedom analysis. If the number of degrees of freedom is equal to 0, that means there are the same number of independent equations as unknown. So you have to have 2 equations, 2 unknown, and in principle, the problem can be solved. So this is why we use that concept of number of equations must equal number of unknowns. That's degree of freedom analysis. It's just been taught in a different way if you've seen that before. If the number of degrees of freedom is greater than 0, what that means is that there's more unknowns than there are independent equations, which means that you need to write additional equations or find ways to get rid of those additional variables. And that's important. So that's going to tell us how many more extra equations we might need to write or how many relationships we may need. If the number of degrees of freedom is less than 0, there are more independent equations than unknown, which means that we have actually overspecified the problem because there are relationships that conflict with each other. And so we either have incorrect labels or we've overspecified the problem. Now, when I write problems, occasionally I do this by mistake because I'm trying to provide the most information possible. But what I will do is I will write a degree of freedom analysis to try and figure out if I have written the problem correctly. We'll go over how to do this in class, but know these different conditions so that we can use them and make judgments about the amount of information that we have in a given problem. When we write equations to perform that degree of freedom analysis, and when we write equations to write a mass balance, we have to have a bunch of different places that we can go to write equations. And the first one is always writing material balances. So when I talk about writing material balances, what I'm talking about is using the general balance equation and simplifying it based on the flow diagram. So that's going to be one source of equations that we write to solve a problem. We can also look at energy balances, and we're not getting there until the end of the semester, but we will eventually write energy balances. We can also write what are called process specifications, which are also relationships between variables. So for example, the fact that density equals mass divided by volume, that's a process specification. So that's an additional equation that can help reduce the number of degrees of freedom so that the problem becomes solvable. We can also use physical properties and laws. We can use physical constraints, and we can use stoichiometric reactions. And a lot of these D through E are going to be later on in the class as the mass balances become more difficult and need more information. So with all of that information that was just provided to you with those examples and how to do degree of freedom analysis, the last thing that we want to think about is what is our general procedure for how to solve a single unit mass balance. First, we need to choose the basis of calculation, which is the amount or flow of one of the process streams. So what are we basing all of our calculations on? Is it the fact that there's 100 moles coming into stream 1, or is it the fact that there's 1,000 mass per time into the second unit, or something like that? And we'll talk about how to pick this in class. You've seen me pick a basis of calculation before when I told you that the total number of grams in a system was equal to 100 to make your life a little bit easier. Many times the problem has specified the basis of a calculation for you and you don't need to worry about it, but in other times we'll need to talk about it. Then you want to draw your flowchart, fill in all the known and unknown variables and your basis of calculation. So draw and label your flow diagrams just like we've been doing. Then you want to make sure that everything that is being asked for is expressed in terms of variables. So try and write equations. If we're given the mass in moles for streams, we want to make sure that we convert to one basis. So if you have all mass and then one of yours is moles, you don't want to leave that moles in moles. You want to translate it to mass. So that's going to be really important as we go forward. We will start with very simple processes that have just mass or just moles, but eventually I'm going to start throwing them together to make them harder problems. So you need to make sure they're on all one basis. Then you want to perform your degree of freedom analysis to see if the problem is actually solvable. Then you want to write out your equations based on the general balance equation, write any relationships you know, and combine them as much as possible. And then you want to circle your variables to solve for. We also have been talking about the fact that we should use back substitution to check our answers, so we should always make sure that we do that using any unused balanced equations. And then we want to solve for any additional variables using our equations. So this is your general procedure to solve for a mass balance on a single unit, and it's actually it's the basis of our procedure for multi-units when we do get there. So make sure that you understand the steps. We will talk about how to perform degree of freedom analysis in class. Make sure that you understand how to simplify the general balance equation, review that if you're confused, and we will make sure that we can apply this to actual processes in class.